Hello and welcome to this webinar from Taylor Hobson. My name's Mike Mills and I'm the Chief Metrologist at Taylor Hobson. This is one of a series of webinars covering basic surface texture and form metrology concepts relating to our products. In this particular webinar, we'll be looking at velocity analysis, which is one of the analysis options on our Roundness instruments. If you have any questions during the presentation, please type them into the question and answer session on your panel on your screen, and I will try to answer your questions at the end of this presentation. So this presentation outlines some of the concepts in velocity analysis, which is a licensed option within our Roundness software. Velocity analysis is a useful tool when measuring some of the components of rolling element bearings, as it can highlight the impact of small amplitude high frequency features that might lead to early failure of the bearing. To begin with, we'll look briefly at the measurement of vibration on a finished bearing assembly, and we'll then look at how some of the individual components could be tested by measuring on a Roundness instrument and analysing using velocity analysis. We'll look at the mathematical background to the analysis and the definition of two key parameters. Finally, we'll look at some of the factors that influence the measurement results. During the presentation, I'll be using some simplified terms and will omit qualifications that will be necessary to make the terminology strictly correct. However, hopefully, this will make the presentation easier to follow. So, testing of REB assemblies. REB stands for rotating element bearing. So that's things like roller bearings and ball bearings. We're now going to look at one method of testing finished rotating element bearings in a production environment. The impact of rotating machinery is huge. Wherever rotating equipment is used, there'll be some form of bearing constraining the rotary motion. And mechanical bearings can be divided into journal or plain bearings and rotating element bearings. REBs take many forms, in particular roller bearings or ball bearings. And for the purposes of this presentation, we'll take the example of a ball bearing, but the principles apply to other forms of REB. Vibration is an important consideration for the life of a bearing. The bearing will transmit vibration that it's subjected to, but vibration can also be generated in the bearing, typically by small imperfections in the components. These vibrations will give rise to noise, wear, and eventually failure of the bearing. It's the aim of the bearing manufacturer to limit these vibrations by controlling the quality of the individual components within economic considerations. For vibrations caused internally to the bearing, the key task is to identify which vibrations are important. Harmonic analysis can be used to identify the frequencies present. To identify the likelihood of a particular frequency causing a problem, for example bearing fatigue, we need to consider the energy in the particular frequency. And that energy is related to the velocity amplitude, and hence the importance of velocity analysis. So as mentioned earlier in this presentation, we're going to use the example of a ball bearing. Aside from lubricant, shields and seals, the bearing has four main components: the outer race, the inner race, the ball bearings, and the cage. Each of these can contribute to vibration in the bearing. Bearing vibration can be tested in a vibration test rig, and this is shown schematically in this slide. This type of instrument is also known as an Anderon meter. The bearing is loaded onto an arbor that's mounted on a precision spindle. The bearing is preloaded by applying an axial force to the outer race. A vibration sensor is placed in contact with the outer race to measure radial vibration in the bearing as it is rotated at constant speed. Different types of sensors can be used, but the output of the center is converted into velocity units, usually micrometers per second. Analysis of the bearing is done in two ways. Firstly, by listening to the noise using headphones or a speaker, and secondly, by the measurement of RMS velocity in 3 bands designated as low, medium, and high. ISO 15242 describes procedures for measuring vibration using such an instrument as I've just described. A typical rotational speed is 1800 RPM, although other speeds are allowed. 1800 RPM equates to 30 revolutions per second, and this means that low to moderate harmonics will be detected within the audible range. For example, acting on its own, a 2 undulations per rev form error would cause a frequency of 60 Hz. The vibration signal is filtered into 3 bands, low, medium, and high. The 3 default bands are shown here for a rotation speed of 1800 RPM. If the rotation speed is changed, then these band limits should also be changed. The RMS velocity is then calculated for each band. Velocity is a useful quantity in vibration measurement as it relates to the energy of the vibration. Before leaving this section of the presentation, it's worth noting the definition of RMS velocity given in the ISO standard. So this quote from ISO 15242, part 1, defines RMS velocity as the square root of the average of squared values of the vibration velocity within a time interval t. So inspection of the component parts of rotating element bearings can help reduce failure of the completed bearings in final testing. We've seen how velocity analysis is used to test the completed bearing assembly, as it indicates the energy in the vibrations across a particular frequency band or bands. The same is true when using velocity analysis in the measurement of the individual components. The results will be different from the completed assembly, but the principle is the same. Velocity analysis can highlight areas where it is likely that there would be problems due to excessive vibration. Because we're dealing with the components, there is a potential to be able to link high velocity amplitudes directly with the manufacturing process. The component parts of REBs have to be manufactured to extremely close tolerances. Surface texture and form need to be controlled. For bearing races, a suitable form tally surf instrument can provide cross-track form checking and surface texture measurement. Within our product range, roundness can be assessed on a suitable Talyrond or Sotronic roundness instrument, depending on the application. When using a Talyrond, velocity analysis is available as a licensed option. This indicates the RMS velocity for the component in user-defined bands in a similar manner to the way the assembled bearing is tested. Before looking at the analysis of the roundness data to provide the velocity analysis result, it's worth reviewing some aspects of the data acquisition system. Now, this has been covered in a previous presentation called Introduction to Roundness Instruments, which is available on our website should you wish to look at this in more detail. The graphic shown here represents the data acquisition path right from the stylus tip through to the computer. The data acquisition system is responsible for initial signal conditioning, for converting the individual readings into a digital format, and for storing these readings for later processing. Signal conditioning might involve amplification and filtering of the signal prior to the converter stage. The filter could be a separate component or a filter that is inherent in the way that the converter works. Sampling of the gauge signal is usually triggered by some feedback of the spindle position. When a roundness measurement is made, variations in gauge deflection are recorded as a function of spindle angle. These variations are a combination of component errors, setup errors, rotational errors from the instrument, and other factors such as noise. Small errors in eccentricity will normally be removed by the analysis. However, other setup errors such as tilt cannot be dealt with readily and so will contribute to the overall measurement uncertainty. Residual spindle errors will also contribute to the measurement uncertainty. Typical spindle errors will mainly impact the lower harmonics, say 1 to 15 UPR. Noise is another uncertainty contributor that will have to be accounted for. So in this next section of the presentation, we'll look at how harmonic analysis is performed and then go on to look at the velocity spectrum, how that's determined from the harmonic analysis. We'll also look at the two key parameters from the velocity analysis. Now, this is not a full review of the software, so only the principles and main results are presented here. Fourier theory can be summarized as any continuous periodic function can be represented by a superposition of sinusoidal waveforms. When measuring roundness, a complete circular component, such as a bearing race, the profile is inherently periodic, and so the profile can be expressed as a Fourier series, as shown here. The Fourier series can be calculated in many different ways. The methods used in a digital computer aim to reduce the computation time by breaking the overall computation into a series of smaller computations and thereby reducing the number of multiplications that are done. The most well-known method of reducing the computation time is the method published by Cooley and Tukey in 1965, which is often referred to as the fast Fourier transform, or FFT. However, this is just one method of reducing the computation time. One of the limitations of the Cooley and Tukey method is that it relies on a dataset that is 2 to the n points long. Data that doesn't meet this criterion needs to be reduced or extended in some way in order to comply. In our Talleyrand instruments, the data length is a multiple of 3,600 data points. Rather than interpolating the data to a power of 2, we use a different fast Fourier transform method that follows the Winograd approach. In this method, the problem is broken down into a number of factors of the target number. For example, a 3,600 point transform can be broken down into transforms of 4, 5, and 9 points, as shown. Having transformed the data into its Fourier components, we have a set of displacement amplitudes for each of the harmonics. To convert this into a set of velocity amplitudes requires a little bit of mathematics. We can operate on each of the sine waves independently. So noting that velocity is the rate of change of displacement, we can obtain the velocity amplitudes by differentiation. We can see the calculation here and see how each velocity amplitude can be derived very easily from a knowledge of the wave number k, the wave amplitude a, and the fundamental rotational frequency omega naught, where omega naught is in radians per second. So writing omega naught equals 2 pi f, where f is the rotational speed in revolutions per second, gives us the simple formula for the nth harmonic as the velocity of the nth harmonic is 2 pi times the frequency times the amplitude times the wave number. The rotational speed is a user-defined parameter entered into the analysis, and in Ultra software it's possible to define a different rotational speed to each defined harmonic band. What is immediately obvious from this result is that the velocity analysis weights the individual harmonic amplitudes by the harmonic number. This means that a high-frequency harmonic with relatively low amplitude might now show up as more significant than a lower frequency harmonic with a similar or even higher amplitude. And this is the value of velocity analysis over harmonic analysis. So velocity analysis results are presented in many ways. One presentation of the results is the velocity graph as shown here. The graph shows the velocity amplitudes in micrometers per second by frequency in undulations per revolution, or UPR, in each user-defined band. The bands are labelled L, M, and H, and these can be broken into 3 subbands as shown here for the bands H1, H2, and H3. 2 cursors are provided to allow the user to interrogate the graph. Summary text below the graph shows the velocity amplitude and wave number for each cursor, and the RMS velocity calculated across the band bounded by the 2 cursors. One might well ask why the velocity amplitude is labelled Vel RMS, but hopefully this will become clear over the next few slides. The key result is the RMS velocity calculated from within a band. We denote this as Vel RMS, and the calculation is shown here. For each harmonic in the band, from wave number L to wave number U inclusive, we calculate the square of the velocity amplitude. These squares are then summed and divided by the number of harmonics or waves within the band. Vel RMS is the positive square root of this figure. An important point to note is that for a single harmonic, in other words for a band where U equals L, Vel RMS is simply the amplitude of the velocity at the selected wave number. This means that in the previous results, where we saw the cursor being labelled as Vel RMS, this is the same as labelling with the term velocity amplitude. There is another parameter defined which is denoted as Vel RS in our software. This parameter is sometimes referred to as RMS velocity, but its calculation is different from Vel RMS. As shown here, Vel RS is defined as the positive square root of half the sum of the squares of the velocity amplitudes within a band. The 2 parameters Vel RMS and Vel RS are only equivalent when the chosen band contains 2 harmonics, i.e. U equals L plus 1. Most importantly, when measuring a single harmonic, i.e. when U equals L, Vel RS is the velocity amplitude divided by the square root of 2. In general, Vel RS and Vel RMS are not the same. It's important then when comparing results from one system to another to know which parameter has been calculated. Let's look at the result of Vel RS when considering a single harmonic. The image on the right shows the sine wave, and the 2 shaded sections have the same area. The height of the rectangle, whose base is 1/2 wavelength, and whose area is the same as the area under the curve in 1/2 wavelength, is A divided by the square root of 2, where A is the amplitude of the sine wave. This, of course, is a well-known result. If we compare this result with the VEL-RS calculation for a single harmonic, and remember that Vk is the velocity amplitude of the harmonic, it is immediately obvious that VEL-RS for a single harmonic is simply the RMS velocity amplitude of that harmonic. If we now look at a band of harmonics ranging from L to U as before, we can compare the results for VEL-RMS and VEL-RS. We can see that VEL-RMS is the root mean square of the velocity amplitudes within the band. And with a little arrangement of the formula for VEL-RS, we can see that VEL-RS is the root sum of squares of the individual RMS velocities. Excuse me a second. The light's just gone out. There we go. That's back. So some measurement considerations. Velocity measurements are used in product and process control. It's therefore important to have some appreciation of the uncertainties that might impact on the results. As discussed earlier, the measurement itself is the sum of component errors and system influences. At low harmonic numbers, for example 1 to 15 UPR, residual spindle form errors might be important. At higher frequencies, noise will be of more concern. Now, noise can arise from the measurement system or from the environment, particularly from floorborne vibration. Ideally, steps should be taken to isolate the instrument from such environmental influences. Remember that the velocity amplitude involves multiplying the harmonic amplitude by the harmonic number. As a consequence, noise of the same harmonic amplitude will give rise to different uncertainties at different frequencies. The data acquisition system also plays a part. We've seen that the data acquisition system will include an anti-alias filter. There is potential for this filter to attenuate higher harmonics. This can be mitigated to some extent by reducing the spindle speed. The gauge also plays a significant part. The gauge and stylus form a mass spring system which will have a natural frequency. Excitation of frequencies near to the natural frequency or close to subharmonics could excite resonance, leading to erroneous results. Again, this can be mitigated to some extent by reducing the spindle speed. Tracking might also be an issue, particularly for large diameter bearing elements. For example, a 300mm diameter component has a circumference of about 940 millimeters. So at 6 RPM spindle speed, this would equate to a surface speed of about 94 millimeters per second, and the stylus would be unlikely to track this faithfully. Again, a reduction in spindle speed might help to mitigate this effect. The stylus tip also acts as a morphological filter and must be chosen to be appropriate to the harmonic wavelength and amplitude. Clearly, the stylus tip size needs to be specified as one of the measurement conditions. The combined impact of many of these issues mentioned previously can be assessed by measuring a multi-wae standard. The standard itself is a cylindrical artifact with multiple harmonic waves machined into it, typically by diamond turning with an appropriate tool servo. There are two types of standard, one using a single ring with multiple harmonics machined into it, and the other using multiple rings with individual harmonics machined into each ring. Both types can be calibrated or uncalibrated. A key advantage of the multiple ring type, as shown here, is that the individual harmonics can be calibrated by means that are not dependent on using a roundness instrument. The measurement system can be tested by measuring the standard at different spindle speeds and noting any variation in the reported harmonic amplitudes. Where the instrument has a single spindle speed, it's necessary to use a calibrated standard and compare the reported harmonic amplitudes against the certified values. So in this presentation, we've looked at some background into the testing of rolling element bearings for vibrations. We've seen how the energy can be related to the velocity in the vibrations and how velocity analysis is used to characterize bearing vibration in different frequency bands. We've looked at the measurement of rolling element bearings on a rotary axis form measuring instrument, and in particular, we've looked at the calculations involved in the velocity analysis. We've also reviewed some items that should be considered when making the measurements, as these will contribute to the overall measurement uncertainty. So that brings us to the end of today's presentation. Thank you for all your time and attention. I'll now try to answer any questions that you might have. So are there any questions from there, Alice?
Oh, sorry. There's no questions, so we can end the webinar now. Thanks, Dr. Mike.
Okay, thank you all very much for your time and attention. Goodbye.